Okay, so you've completed the vocab here. So as a reminder, an exponential function has this format: y equals a times b to the x. Again, where a is not 0, b is not 1, and b is greater than 0. And then raised to the x power. The reason b isn't 1 is because 1, times 1 times 1 times 1 is still going to just be 1. So that doesn't create any kind of exponential function. So again, like we have examples here, y equals 2 to the x. So we plug in something for the exponent of x and generate a y. And here, y equals negative 2 to the x. Again, as a reminder, the negative is not go along with the 2. It gets applied afterwards. Similarly here, y to the 1/2 x, you're going to see it go down. And notice here the difference. Here is a number larger than 1, right? This goes up, this goes down because of the negative. Here is a number smaller than 1, so it's going to cause this to come down. And in this case, the negative causes this one to go back up. So these are kind of a pattern to look for as you're working with each of the different ones here. The trick to noticing an exponential function when you are working with the just looking at the input and output is to notice a constant difference. Here, notice each time going up by 1. Here, again, being multiplied by 3. So we have a certain ratio that we can see here each time. So that's sort of the key. And if you're not sure, you can graph this, right? You could plot these points. If I were to guess, if I were to make sort of a guess grid here like this, I would go back and so we'd have 0, negative 1. Hang on, I'll make it a little bit bigger here. There we go. So 0, negative 1, 1, negative 3, 2, negative 9, right? 3, negative 27. So you can see it's going to have this kind of flow to it. And eventually we'll get to the point where we are going to write exponential functions using just a set of points, and you're going to come up with it. That's kind of fun, right? So taking a look here, we'll look at the example B. Look at that right here. Is this one an exponential function? And notice it's not, because the variable is here in the equation as opposed to being the exponent. So we know that one immediately is not an exponential function. So it should be, the x should be here. So if we're 3 times 2 to the x power, right, that would certainly represent an exponential function. But this does not. So recognizing one here, again, taking a look, we can see, certainly up here, go by 1, 2, so adds 1 each time, right? On the bottom, though, are we getting that? Are we getting an exponential function? From here to here, it's multiplied by 1, right? Here to here times 3. Here to here, no. I mean, I'm not seeing that we are multiplying each time by something, so it's certainly not growing in that fashion. And again, if you're not sure, go back and look at the previous example here where we discussed that. On this part, this is most certainly an exponential function. 3 times 6 to the x power. Again, remembering the rules here that this can't be 0. This has to be a certain number. It can't be 1, right? And it has to be greater than 0. And then raised to the x power. So most certainly an exponential function. Here, in my opinion, is one of the fun parts of this. This is showing growth. So suppose 30 flower beetles are left undisturbed in a warehouse bin. So I'm assuming the bin full of flour. The beetles' population doubles each week. The function f of x, or that's your y, equals 30 times 2x, gives the population for x weeks. About how many beetles will there be after 56 days? Notice this is weeks here, so you have to turn that that 56 days into 8 weeks when we think about the problem. So pay attention for little things like that I try to catch you up on. So anyway, so we have y equals, we're going to f of x equals 30 times 2x. Plug in that 8 weeks because 56 days is 8 weeks. And we get 7,680. So at 56 days, there will be 7,680. One thing to note in here is that there was certainly probably 30, right, beetles to begin with. So that's an important bit of information. This problem is extremely similar to the last one. This is an initial population of 20 rabbits, triples every half year. The function f of x equals 20 times 3 to the x. Gives the population for x half-year periods. So again, please note that X is half-year period, so 6 months. How many rabbits will there be after 3 years? Before we start, you need to note that 3 years equals 6 half-year periods. Okay? So, our function, f of x equals 20 times 3, and this will be to the 6th, because we have 6 half-year periods in 3 years. So, f of x equals 20 times 729, which gives us, so f of x is 14580, and that'd be rabbits, like we have down here. Okay, so time to graph this thing. I think we've talked about this before. This might be the example as well that I used in the vocab video. So, again, this is plug and chug stuff, right? You have a graph, right? And so an XY coordinate, and you start picking points. Now, again, I recommend picking points that are easy to work with, and provide nice numbers, ones that are easy enough to graph. So we start out here by plugging in -2. Run that through this, so -2 here, so 2 to the -2 power times the 3, we get 3/4. Plug in a 1, we get 1 1/2. You're not sure? I mean, take a look here. I've done the work's already done for you. Plug in a 0, you're going to get 3, right? Plug in a 1, and you're going to get 6. Plug in a 2, you're going to get 12. So you plot each of those points. So -2, 3/4, and some of those you have to do a little bit of estimating when you are graphing, and I understand that. -1 is 1 1/2, 0, 3, 1, 6, and 2, 12 are the only ones that fit on this graph. So again, connect them with a nice, smooth curve after you plot the points. Okay, on this one, we're just going to go ahead and plug some numbers in. What this looks like then, we're going to have an X and a Y chart. So if you're not doing that, do that. And I'm going to pick some numbers to put in there, ones I know that are easy to work with. So -2, -1, 0, 1, and 2. When I plug those in, again, what that looks like taking 0.5 to the third power, right? 0.5 times 3 to the x power, and again, in this case, my x is -2. So that means it's 0.5, technically over 3 squared, or 0.5 over 9, which is actually about 0.06 if I round. Again, some of these are going to be small enough, tough enough to graph. Being close is probably fine there. So if I put in -1, so that becomes 0.5 over 3, or about 0.17. And then put in 0, that's 0.5 times 1, which is 0.5. 1 becomes 0.5 times 3 to the first power, which is 1.5. And then stick in 2, and that's 0.5 times 3 squared, just 0.5 times 9, which is 4.5. And now we just graph them. So -2, 0.06 is going to be like right here, right? -1, 0.17, like this. 0.5. 1, 1.5. And 2, 4.5. So 1, 2, 3, 4.5. Again, the idea is you can make a gradual curve out of this. And it's going to look like this. And up like that. And that's what I expect to see for a graph. So in this one, we're going to notice what a negative coefficient, so almost the exact same thing, but it's -0.5. So a negative coefficient is going to do. So if you think about the work on the last one, I'm going to pick the same points, by the way. It's just going to turn everything negative because you're going to multiply. The powers didn't change, right? So you're going to that 3 to the -2 is going to be, put 9 in the denominator. It's going to be -0.5 then over 9 divided by 9. So it's going to be -0.06. And again, plugging in the -1, so you're going to get -0.17. Plug in 0, you're going to get -0.5. Plug in 1, and you're going to get -1.5. And plug in 2, you're going to get -4.5. So again, if you're not certain on that, sit down and do the actual math. It's going to take the last one, just turn them negative. So let's go ahead and plot those. And again, what does that look like? So -2, Negative 0.06 is going to be right down here. There we go, switch colors there. And negative 1, negative 1.7, like there-ish, not quite maybe. 0 is going to be negative 0.5. 1 is going to be negative 1.5. And 2 is going to be negative 4.5. So 1, 2, 3, 4.5. Again, what this is going to look like is a nice gradual curve going like this, shooting up. This one's going to get smaller and smaller, closer to 0 on that left side. So, alrighty, there you go. There's that one. I'm sure you've already guessed that I can most certainly turn this into story problems. Loads of fun, right? So, computer mapping software allows you to zoom in on an area to view it in more detail. The function, again, f of x, or y, 100 times 0.25 to the x models the percent of the original area the map shows after zooming in x times. So again, I assume these would be static zooms. And this one, the idea is that this graph is not going to be connected dots because you don't zoom in 1.5 times. It can be 1 click, 2 clicks, 3 clicks, so on and so forth as it zooms in on you. And notice here, we certainly aren't going to plug in negatives. You don't do negative zooming. So zooming at 0, again, plugging that in 100 times, 0.25 to the 0 power. Again, remembering 0.25 to the 0 power is the number 1. So 1 times 100 is 100. So 0, 100 is our ordered pair. Plug in a 1. So 0.25 to the first power is 0.25 times 100 is 25. So we get the 0.125. And you can see so on and so forth. So this one, again, is going to be individual points. You're not going to play connect the dots here because you zoom in 1, 2, 3, 4. You're not going to zoom in 1.5 or 2.36, things like that. So it doesn't make sense to actually connect the dots in this one. Okay, so here we just want to know, so it says you can zoom in and out of it for view a larger area on the map as well. Zoom out with it, I'm sorry. The function f of x equals 100 times 4 to the x models the percentage of the original area the map shows after zooming out x times. So again, it's not a gradual thing, it's step by step, so it'll zoom out 1, 2, 3, right? Graph the function. What is the percentage change in areas each time you zoom out in part? So, f of 0, we're going to actually plug that in for you to make sure you recognize that. F of 0 equals 100 times 4 to the 0 power, which, by the way, is 100 times 1, which is 100. F of 1. F of 1 is 100 times 4 to the first power, which is obviously going to be 400. And f of 2 is 100 times 4 squared, which is going to be 1600. And again, you can see you've graphed that up here. If you take a quick look, graph that right up here. So 0, right, 100, and 1, 400, and 2, 1600. And again, these are dots. You do not connect them because you can't zoom out a portion like 1.5 times, things like that. It's step by step. As far as how much it's changing, right, this is times 4, right? Times 4. Notice that's kind of indicated by this if you take a look there. So you would expect the next one to be 1600 times 4, if you could zoom out even farther. Just to make sure we understand, this actually right here is 100%, 400%, 1600%. So this is full, right? Times 4 times 4.